All right. We'll get started with one person in the room. The only kind of major announcement that I know about, and it's not all that major, the Sacs team is on campus, but they're on the Birmingham campus today. Yesterday they were on this campus. I understand at least part or most of them or whatever. And as far as I know, they're on Birmingham and maybe Birmingham only today. So we may be through with them on this campus. I never saw them, but they were in meetings with administrators and things like this. And then I understand there's a luncheon today for select people, which I'm not one, so that they're going to have lunch with them. And so I'm hoping that means everything's hunky-dory and they're on their way out. So, but if not, if you see a team running around, be sure to treat them nicely. Okay, of course you would. Let's see, any other things I know about, not that I can think of. So let's move on. Any questions on anything we've covered so far? Okay. Now, we're in Chapter 9, Infinite Series, but we're actually in 9.1, which is sequences. We're not quite in series yet. We're going to get there. The subsection we're in is monotonic sequences and bounded sequences. We talked about monotonic earlier, last time, so now we're on to bounded. And I was thinking we had already done this, but I guess not.
We had started it, but we never made it to example 9.
To what?
We never made it to example 9.
Example 9, right. Did we do this definition here?
Yes.
We did. Okay, I thought we had, but for some reason my mark's on the wrong place. I must have forgotten to mark. Did we do this slide?
I don't think so.
Okay. So let's pick up here. Okay. Now this is based on this definition of bounded sequences. Okay. And one that's bounded period without saying above and below, bounded both above and below. So one important property of the real numbers is that they are complete. Real numbers. Obviously, real numbers are not bounded, okay? They go infinitely large, infinitely small, they're not bounded. But they are complete. Now, informally, this means there are no holes or gaps in the real number line. Now, you might say, wait a minute, how about complex numbers? Well, they're not on the real number line. So, the real number line is complete. The real number system. Okay. Informal, that means, okay, right. The set of rational numbers does not have that completeness property because you can have, I forgot to take that off yesterday, and I bet you it's sealed in there. Last time before too, so slipping up. Okay. Set of rational numbers. If you consider the real number line here, let's say we have, for instance, the square root of 2 is about 1.414. The square root of 3 is something in between that. Well, I'm sorry, rational numbers. Rational numbers would be ratio of, say, 1.4 and 1.5. Those are both rational numbers. And you can keep going as far as you want to with the square root of 2, but you'll never hit the square root of 2 in between as a rational number between square root of, between, say, 1.4 and 1.5. No matter how much you narrow with rational numbers, you'll never get to square root of 2 because it's irrational and it's on the real number line, so it's not complete. Rational number does not have that completeness property. The completeness axiom for real numbers can be used to conclude that if a sequence has an upper bound, then it must have a least upper bound. In other words, if you find some limit up here and you know you can't go above that, then there's got to be, if that's not the ultimate limit, there's got to be a least upper bound. That you would have an upper bound that is less than all the other upper bounds for the sequence. And that's because in the real number system, it's complete. There's got to be one that's the least upper bound and no more than the one we have. Okay? Now, just as a refresher, notice an upper bound, you have the equal sign there. The n is either for the upper bound, a sub n is less than or equal to that m. Okay? So whatever your m was as an upper bound, keep it going down until you have it equal to. If that m is always greater than all the a sub n's, keep on going down until you find that one that makes it equal to one of the a sub n's. Then that's the least upper bound, so to speak. Now, that's not how you would normally do it, but that's conceptually how it's done. It's upper bound that is less than all the other upper bounds in the sequence. So here's for example. The least upper bound of this sequence, a sub n, is n over 1 plus n. Okay? 1 over 2, 2 over 3, 3 over 4, 4 over 5, and all like that. That's going to be the number 1. You can't pick a number that is less than 1 that you can't find the rational number that would be greater than that. But 1 is. These are getting closer and closer to 1, closer and closer to 1, never going to reach 1. So it's not going to be one of those it's equal to, but you'll never, they get so much closer that 1 will be your least upper bound. Now, sticking on the end of that is theorem 9.5. Bounded monotonic sequences. If a sequence a sub n is bounded, now remember bounded means from above and from below. And is monotonic, okay? So then it either is increasing or decreasing, not ever bouncing back and forth, then it has to converge. If it's bounded and monotonic, then it converges. Now this really has very little to say with the least upper bound. Why they put it on the same slide, I don't know, but it's okay. They're both true statements here. Okay? If a sequence a sub n is bounded, meaning it has an upper and lower bound, and it's monotonic, meaning it's increasing only. Now, for instance, the log function, that's monotonic, but it doesn't have an upper bound. So therefore, that does not converge. Something like this does have an upper bound. That upper bound is 1. This is monotonic, strictly increasing here, and always is going to increase. It never exceeds, never even reaches 1, so it converges to 1. So that is an example of it, so sort of convenient it was on that page. All right, so here's example 9, at least the A part. The sequence a sub n is equal to 1 over n is both bounded and monotonic. So it says it must converge. What does it converge to?
It's getting closer to 0.
Yes, absolutely. It's converging to 0. Never reaches 0, but it's bounded, and 0 happens to be its greatest lower bound. We didn't mention that, but there is also that. And this is a monotonic sequence because, now, of course, you have to be starting with 1. You can't start with 0. And that all bets are off on this. Starting with 1, 1 over 1 is 1. and 1 over 2 is 1/2, 1 over 3, 1 over 4, and 1 over 5, and they just keep getting closer and closer to 0. Never reaches there, so it does have to converge, and it converges to 0. Now, the divergent series, B sub n, I hate to tell you that, I should have just given you the sequence and then ask you. N squared over m plus 1. It's monotonic, but it's not bounded. It's bounded below, because if n is 1, this would be 1 over 2, so 1/2 would be the greatest lower bound, but it's not bounded above, because look at the ratio of the leading terms. That would be n over 1. And that, as n goes to infinity, that's going to infinity. Monotonic, always increasing. Like we said, 1 over 2, and the next would be 4 over 3. The next would be 9 over 4. It's increasing, and actually the gap gets wider and wider and wider. So that's a divergent sequence, monotonic, always increasing, not bounded both ways, bounded from below, but that doesn't help any. It has to be bounded above and below. Okay, now here's one. This divergence, this series, sequence, C sub n, is minus 1 to the n. What does that do? N is equal to 1, that's?
It's going to alternate signs.
Yes, minus 1 plus 1, minus 1 plus 1, minus 1 plus 1, minus 1 plus 1. It's bounded above and below, but it's not monotonic. So therefore, now, our theorem didn't say that. Now, so let's go back to the theorem. If a sequence is bounded and monotonic, then it converges. Now, what it doesn't say, if it converges, it's got to be bounded and monotonic. They didn't say if and only if. They just said if this, it converges. So, just because it's bounded, of course this one's not monotonic, that doesn't mean it couldn't possibly converge. Yeah, I think it does. It has to be bounded to converge, so never mind that. But if it's bounded and monotonic, it's got to converge. Yeah. I think you can be bounded and not monotonic and still converge if you were getting closer and closer, up and down like that. Just put a minus 1 to the nth in front of that one, and you still are converging, but it wouldn't be monotonic. It would be bounded. It would be not monotonic. That doesn't mean it's going to diverge, because you can do the same thing. Just put this in front of that, and you have a bounded sequence that's not monotonic, but that one would converge. This one does not, because it just bounces back and forth between the two, never approaches anything. Whoa! That is the last example. That's the last slide. Homework exercises here would be any of the odds 5 through 9. They're all at Calc Chat. 9's at Calc View. Number 11's at Calc Chat. I would do all 4 of 13 through 16, even though only 13 and 15 have answers in the back and are at Calc Chat. But I think you can probably pick up all 4 of those. Hopefully you can. They're matching. Then do either 17 or 19. They're both at Calc Chat. 21 or 23. They're both at Calc Chat. 21's at Calc View. 25 or 27. Both at Calc Chat. Any of the odds 29 to 43. They're all at Calc Chat. 29's at Calc View. Any of the odds 45 to 51. They're all at Calc Chat. 49's at Calc View. 53 to 59, they're all at Calc Chat. 53's at Calc View. 61 or 63, both at Calc Chat, and then 65 or 67, they should both be at Calc Chat. You can explore doing 69 or 71, they should both be at Calc Chat. 73 is using the sequence, it should be at Calc Chat. 75 is a proof, it should be at Calc Chat if you're interested in the proofs. 77 and 79 are true false, they should be at Calc Chat. Pretty famous series is mentioned in number 81. You've already written your paper, but for people who haven't, hint, hint, then the Fibonacci sequence is given and talked about in 81, and that's associated with several really interesting concepts. One being the golden ratio. Have you ever heard of that? Have you ever heard of Fibonacci series? Oh, sequence. It's he was studying the progeny of rabbits, and Fibonacci encountered a sequence now bearing his name, and it's defined recursively. You can't say what the nth term is without knowing the previous term, two terms in fact. So it's a pretty interesting. Let me just write down the first term for you. Pretty sure it starts with 1. Yeah. First term is Fibonacci series is 1. Okay? Now the next term is the sum of the previous two terms. And of course, the previous term is 1, previous term of that, there isn't one, so it's also 1. So you tell me what the next term is.
The sum of the previous two?
Yeah.
So that's 2.
2. Next.
3.
Next.
5.
Next.
8.
Next.
13.
Okay. And it keeps on going that way. All right. They say write the first 12 terms. I stopped well before that. And then it has another sequence there it's wanting you to do. But anyway, that's the Fibonacci sequence. Now, where the golden ratio comes into play, it can be defined the first 10 terms of the sequence defined by, and I assume they mean the A's that you used before, A plus 1 over N. So here would be your B sub N's, which is A plus 1, A to the N plus 1. Over A sub N. The Fibonacci sequence. So the first of this, the first one would be 1 over 1. Next would be 2 over 1. The next would be 3 over 2. 5 over 3. 8 over 5. 13 over 8. Okay? Now, if you were to they say do 10 terms of it, so you could do that if you wanted to. That's why you needed 12 of the previous one. And then they say the definition that we just did for that part, it says show that B sub N is equal to 1 plus 1 over B sub N. So this B sub N is equal to 1 plus 1 over b sub n minus 1. Yeah. All right, let's take a look at that and see what we get. So you have to go to the second one for this to make any sense too. So that would be 2 is equal to 1 plus 1 over 1. So sorry. That certainly works. Then 3 halves is equal to 1 plus 1 half, which is true, right? 5 thirds is equal to 1 plus 2 thirds. And that's certainly true. And you can keep on going and show that does fit the bill. Okay? Now, what the golden ratio is, given the symbol rho, the ratio I guess, can be defined as the limit as n approaches infinity of b sub n. Okay, these b sub n I just did at the bottom here. Sorry. All right, now, so what you get to is rho is equal to, very similar to what you did before, 1 plus 1 over rho, which is rather bizarre that it would equal itself, be part of its own definition. It says solve that equation for rho. Well, multiply both sides by rho and you get rho squared is equal to rho plus 1. Okay? And that'd be rho squared minus rho minus 1. Sorry. This is terrible. So you can play around with this and solve that if you can. Play around and see what rho is. That's the golden ratio. Now, what difference does that make anyway? Well, a lot of things, an incredibly lot of things, are proportioned according to the golden ratio. Basically, the human body is. And there's a way to define that. The things that are incredibly pleasing to the eye, for instance, the Parthenon in Greece, ancient building there, has columns all around. Its proportions are the golden ratio. And it is just always, if you look at the spiral of a conch shell, you'll find the golden ratio in that. Sunflower seeds, they also form in a spiral. The golden ratio is in that. It just is incredible how many things in nature are tied up with the golden ratio, and that comes out of the Fibonacci series. So anyway, it's a fascinating subject. You've already written your paper, but others listening hopefully will maybe, oh, look at this. We've doubled the class size in one fell swoop. Okay. We just finished 9.1. I was talking about some of the exercises to do, and I got stuck on 81 with the Fibonacci series. You can go back and listen to it, but we were just ending it. It's an incredibly powerful or amazing the applications you can find to that golden ratio that comes out of the Fibonacci series. Continuing, you can do number including 81, 83, 85, any of those. They should be at Calc Chat. And then Calc View, 87 or 89 are both proofs. They should also be at Calc Chat. The Putnam challenges are completely up to you if you're interested. I assume they're at Calc Chat too. I've not ever bothered to check. So, anyway, any questions on 9.1? All right. That did end the section in the slideshow, so we'll discard that and pick it back up in 9.2. And I'm sorry, my cough the cough seems to be worse today. Everything else seems to be better, but the cough is just really giving me fits today.
Do you need to go take a water break?
Possibly, but let me go a little bit longer if I can. Probably need to clear the head break, and I'll get water when I do that. Do you need one?
No.
Okay, all right.
Don't work yourself too hard.
What's that?
Don't work yourself too hard.
Okay, thank you. It'll all get out in the wash, hopefully. All right, we're continuing Chapter 9, Infinite Series. We're now moving to 9.2, which finally is series and convergence. Okay? 9.1 was strictly sequences. It's easy to get them confused, and maybe what we're going to do right now is going to make them even more confusing, but they are intricately related to one another. Okay? So, our objectives here are to understand the definition of a convergent infinite series, and we'll use properties of infinite geometric series, which are important ones, and we'll use the nth term test for divergence of an infinite series. Unfortunately, we don't have one for convergence, but we do have one for divergence. Okay. So, infinite series. First big subtopic in this section. One important application of infinite sequences is the representing infinite summations. So basically, informally now, if A sub n is an infinite series, like we did with the sequence, like we did before, that's what the braces here, basically it's a set of numbers. Set of numbers, usually with some rule that determines what the next one is. Okay? The rule may be strictly algebraic rule. It could be something based on the previous terms, which would then be a recursive definition. Okay? But this, now, if that's an infinite sequence, A sub n is an infinite sequence. If you sum those terms, rather than just listing the terms, you add them together. That's what makes an infinite series. Okay? So it's the summation of n equals 1 to infinity, and A sub n. That sequence that we had in the last time, and now what we're going to do is add each of the terms. A sub 1 plus A sub 2 plus A sub 3 plus A sub 4, all the way up to A sub n, and it keeps on trucking infinite. Okay? So, that is what we call an infinite series, or simply from now on we'll probably just call them a series. We assume they're going to infinity. Now, if you think about it too hard, okay, just because something converged as a sequence won't guarantee that it will converge as a series. The reason is you're adding things to it. You're not just listing them. So 1 over n certainly is converging as a sequence, but we'll learn that 1 over n does not converge as a series. So the numbers, A sub 1, A sub 2, A sub 3, and so on, just like we said, they were the terms of your sequence, the elements in your sequence, they are now also the terms of the series. Because by algebraic definitions, anything separated by plus or minus sign is a term. Okay, so those are the terms of the series. For some series, it is convenient to begin the index at n equals 0. We didn't typically do that for sequences, but now there will be times we'll do both. Or even some other integer. This is rare, but you can start it at -3. You can start it at 17. You know, you can start at any integer, not 3/2. That won't work. Okay, but start the end at any sequence, at any integer, and it could be 0 or something before or after 0. As a typesetting convention, it is common to represent an infinite series as summation of a sub n. Now, notice what they've left off here, where it begins and where it ends. But we're assuming it's infinite, so it's going to end at infinity. We'll usually assume it's starting at 1 unless we're told otherwise. Okay? So that's how we distinguish. That's how we represent a sequence with the curly Q on either end. Those are called braces. Either end. That just indicates it's a set of numbers that have some rule with it. Okay? And usually the n is going to infinity. Usually with a sequence starting at 1. Okay? Then to do a series is the summation of those a sub n. As you're adding all those up, the summation. Okay? In such cases as that, the starting values for the index must be taken from the context of the statement. Okay? Here's dramatic. Increase the class size by 50%. Okay. Now, just as we talked about in the last section what a sequence was, we just defined what a series is. It's the sum of the elements of a sequence. Now, to find what the value of the sum is, consider the sequence of its partial sums. So we're going back to the sequence again. So the first in this sequence, S of 1 would be A sub 1. Okay? But S of 2 would then be A sub 1 plus A sub 2. S of 3 would be basically S2 plus A3. S4 would be S3 plus A4. Yeah. So we're back to another sequence here. Okay? It's a sequence of partial sums of that series. Okay? And S of n would then be the series. If that sequence of partial sums converges, then the series is said to converge. It has the sum indicated in the next definition. We haven't gotten to that. If, however, the sequence of partial sums diverges, then the series is considered to diverge. Okay? So, basically, to find what the series is, we look at a sequence of partial sums. So here's a definition of convergent and divergent series. For an infinite series, the summation from n equal 1 to infinity, or any other place you want to start it, it's always going to infinity, a sub n. The nth partial sum is a sub 1 plus a sub 2, all the way up to a sub n, summing all those together. If the sequence of partial sums now is a sequence again, now notice they put this as a capital S. Before that, usually we use what's in here as a lowercase letter. Didn't have to, but we usually did. But now we're going to do this because this is now a partial sum. Okay, so if the sequence of partial sums converges to some value capital S, then the series that you got from that also converges, and the limit at S is called the sum of the series. Sorry. So S would then be the sum, the infinite sum of that entire series would be infinity on top. If, however, S of n diverges, this sequence of partial sums, then the series diverges. No hope for it whatsoever. Okay? So, series is the sum of a sequence, and then you use the partial sums of that series to form a new sequence. And that's the one we evaluate to see if the series converges or not. Okay? Now let's see if this next. They do have a little blurb at the bottom. Well, they have a blurb on the side and a blurb at the bottom. I'm sorry, my throat's hurting now, finally. The study of infinite series was considered a novelty in the 14th century. 14th century. Logician Richard, Swiseth, whose nickname was Calculator, solved a certain problem here. And he found out that the sum of that was infinite series was 2. Now, why they just put that in there, I don't know, but it does give you a potentially other paper topic. Who in the world was Richard Swiseth? That's how I think you pronounce that. So, anyway, that's there. Then underneath this definition, it says, as you study this chapter, you'll see that there are 2 basic questions involving infinite series. The first, does the series converge or does it diverge? Now, this gives you rules for that, but these are not always easy to calculate, okay? Now, the second question, when it does converge, what is the sum? What does it converge to? Okay? Those questions, this is quite an understatement, are not always easy to answer, especially the second one. Okay? So, let's see what we can do with example 1. Here is a series, and it's this sum, sorry, from n equal 1 to infinity of 1 over 2 to the n. Your sequence would be 1 over 2 to the n. We know that converges. We know it converges to 0, and it gets there really quickly. The question here is, does the series converge? Because that starts with when n equal 1, that would be 1/2. When n equal 2, that would be 1/4. When n equal 3, that would be 1/8. N equal 4, that would be 1/16, and so on. Okay? Now, that's the series. They started with the first partial sum. What would be the second partial sum? Not that hard to do. What would it be? 1/2 plus 1/4. Come on, y'all can do that. 3/4. Okay? S of 3 would have been 3/4 plus 1/8, which would be 7/8. Okay? Oh, we have Ryan here. Okay. S of 4 be 7/8 plus 1/16. 15/16. Can you see a pattern here? S of 5. (31 30-seconds). Okay? Let me suggest to you what S sub n would be. Okay? The denominator would be 2 to the n, right? 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, right? And the numerator would be 2 to the n minus 1. Not n minus 1, but 2 to the n minus 1. It's one less than that, right? That's what it's been every time. So the next S sub 6 would be 63/64. S sub 7 would be 127 over 128. Okay. Now, the question is, does that converge? Yay or nay? Yes, it does. The sequence converges. It's monotonic, and it has an upper bound. What's that upper bound?
It's getting close.
Yes, it would be 1. So it converges to 1. So there are the partial sums, and it does converge, and it converges to number 1. All right? Let me erase what I've done, we've done, and let's see what they go from here. S of 2 is 1/2 plus 1/4, which is 3/4. S of 3 is that 3/4 plus 1/8, which would be 7/8. S of 4 would be, it gets over to n. That's real helpful to write it that way. You don't really see anything coming out of it. But this would be 2 to the nth minus 1 over 2 to the nth, just like we said. Okay? The denominator is always 2 to the nth, and the numerator is always 1 less than 2 to the nth. So because the limit as that goes to infinity, the nth term goes to infinity, this over this is 1, and we left with 1 over 2 to the nth, which of course that's going to 0. So this would be 1 minus 0, which is 1. Follows that the series converges and its sum is 1. Make sense? All right. Let's look at the B one. I can almost guarantee you this will get a little more weird, maybe difficult, I don't know. The summation from n equal 1 to infinity of 1 over n minus 1 over n plus 1. Okay? Well, the first one would be 1 minus 1/2. That would be 1/2. The second one would be 1/2 minus 1/3. The next one 1/3 minus 1/4. The next one 1/4 minus 1/5, and so on and so on and so on. Okay? Now, does anyone remember that from a previous life? May not. I don't remember it. We may not have done this. Okay? But what do you notice here? Especially if you remove the parentheses, because they're really not doing any good. You get a minus 1/2 plus 1. That's 0. Minus 1/3 plus 1/3. That's 0. Minus 1/4 plus 1/4. That's 0. And it keeps on going until the nth term would be, all you have left is 1 from here minus 1 over n plus 1. And as n is going to infinity, this is going to 0, so that also has a limit of 1. Right? Okay, I believe that was called a telescoping series. Okay, yeah, they say that later on. Make sense? Yay or nay? Well, that was one. I mean, you mean of another telescoping series? You could just about do anything like this. This one would not converge if you had n minus n plus, let's see, 1 plus n plus 1 minus n plus 2 plus n plus 2 minus n plus 3. And you kept on going like that, again, that would be a telescoping series. But that one would not converge because as n is going to infinity, that's exploding. within the denominator, it converges. Okay, but that is just yet another example. It does converge, this one, the one they gave us, and its sum is 1. So far they've given us pretty easy ones. Let's do the C. Oh, because the limit, no, I'm going to erase my stuff so you don't get confused, especially Dawson, since he just came in. I don't want him to get confused any more than he would be. Okay. Because the limit of S sub n, as n goes to infinity, this is going to 0, just left with 1, because of that. The limit that the series does converge, and its sum is what it converges to, 1. All right, for those who just have come in, section 9.1, we dealt with sequences, okay? Sets of numbers, usually having some rule about them, okay? And we talked about whether sequences converged or diverged or whatever. Okay. Section 9.2 is talking about series, which a series is a sum of a sequence, okay? Just because a sequence would converge doesn't guarantee that the sum of that sequence, because you're adding things to it, would converge. Certainly, if a sequence diverge, adding them together is going to diverge even worse. You have something going that way. We haven't gotten there yet. But then we're talking about what does a series then, does it converge or diverge? Well, how you do that is look at what they call the partial sums of that series. And the partial sums make up a sequence, and then if that sequence converges, then the series converges. And what it converges to is what the sequence is. So that's series converges to. So that's what we were doing there. Now, here's a series. The summation of n equal 1 to infinity of 1. Okay? Now, if you were talking about the sequence, 1, 1, 1, 1, 1, 1, sequence certainly converges, right? To 1. Does the series converge? No. 1 plus 1 is 2 plus 1 is 3, 4, 5, 6, 7, 8, 9, 10. If you're going to infinity, it just keeps getting larger and larger and larger. It's a set of all real numbers, basically. That diverges because the S of n, which is n, okay, as n goes to infinity, the sequence goes to infinity. Sequence partial sum diverges because that does not converge to any fixed number. Getting larger and larger, the larger n does. Okay. The series we did earlier in B was a telescoping series of the form B1 minus B2 plus B2 minus B3 plus B3 minus B4 plus B4 minus B5, and so on. You can eliminate these and these and these and these. All the pairs there, you're left with just B sub 1 minus B sub n. Okay? If B sub n converges, then this will converge. Right? Is that right? Yeah. Okay. Note that B2 is canceled out with the second term, B3 by the third, and so on. So what are we getting at here? Because the nth partial sum in this series, partial sum would just be S of n would be B1, whatever that first term was, minus B n plus 1. That last term in the series. Okay? Of all the others in the middle did. It follows that the telescoping series will converge if and only if B sub n approaches a finite number as n goes to infinity. So the B sub n has to approach a finite number. It can't keep getting bigger. Okay? It has to approach a finite number. If this is a finite number, then whatever that number is, subtract it from B1, you've got your limit. And the value of the sequence, of the series. Moreover, if the series converges, that does go to a fixed number, then the sum will be the sum of that series, S, be B1 minus whatever that limit is. Because that has to convert, this has to approach a finite number as n approaches infinity. So whatever that number is, then subtract it from B1. That's the partial sum. Okay. Now, they have a little blurb at the left of what they just said there. To learn more about the partial sums of the series, see the article 6 Ways to Sum a Series by Dan Coleman in the College Mathematics Journal, and he even gives you a link to go to get to it. Now, before we move to geometric series, we have example 2 coming up. So let's see if we can find some white space to do example 2. Find the sum of this series. The summation of n equal 1 to infinity of 2 over 4n squared minus 1. Find the sum of that series. All right, how would you proceed? Of course, what you could do is what we have done. Start writing down the individual terms of the series, the sequence of those terms, add those together and see if we can come up with a pattern. They're suggesting, and it's a good suggestion, let's do with it what we can first. Our a sub n here, this sequence that we're dealing with here, is 2 over 4 to the n, 4n squared minus 1, right? That's what the nth term in that sequence would be, okay? Let's see if we can figure out some things about it, okay? What's one thing that pops into your brain when you see this? Anything? Especially the number. Yeah, there's a minus sign there. Yes, you can factor it. Now, how does that factor? Oh boy, you do it the hard way, don't you? That's going to leave minus 1/4 then. You can do it that way. It's certainly legal in most states, but easier than that. This is a perfect square, isn't it? Yes, 2n plus 1 times 2n minus 1. Okay. Now, what does that look a lot like? Think back to integration techniques. Remember we did, of course, substitution and substitution, those kind of things, and we did integration by parts. We did trig substitutions. We did trigonometric integrals. There's one other we did. I have to talk to your Cal 2 instructor. Cal 1 instructor, sorry. Wait, that was this term, wasn't it? I am your Cal 2 instructor, okay? What was one of those techniques that we started off looking just like that? Ah, yes, you're getting it. We only need 2 of those. A over 2n plus 1 plus B over 2n minus 1. What do we call that technique? I really don't know where the technique's name came from. I understand the second part of the name, fractions. What I don't know is why they call it partial fractions. But that's what it is, partial fractions. Okay? Now how do we proceed from here? Yes, and what is common denominator? Every term by that. All right, good deal. Over here, everything in your denominator goes out, as it does everywhere, but it leaves a thing or two in the numerators. Okay, so what we get here, all that's left here is 2. What we have here is we'll leave it as a unit for now. A times 2n minus 1 plus B times 2n plus 1. Now, why would I want to leave those written in that ugly looking form? Remember, the next step was one that always seemed questionable to me, but it works, so we do it. Pick an n. And then that will be beneficial to you. Anyone think of what that might be? N equal 1/2 would be a good choice. Okay, this side is still a 2. This side becomes what? 0 plus B times 2. And guess what B would have to be then? 1. Okay? Pick another n. That works so well. Negative 1/2 works splendidly. Your left-hand side is still 2. Your right-hand side now becomes not quite. Negative 1/2. 2 times negative 1/2 would be a minus 1. Minus 1 would be a... Yeah, the right side. The first term on the right side. A times 2 times a negative 1/2, right? Would be a negative 1, right? Minus 1 is negative 2a. Yay or nay? Okay. And then the next one would be 0. Okay. So that yields A being equal negative 1. Okay, let's go back to where we started. That can I erase this for now? Because I don't have much room. I'm going to erase all my scratch here. All the effort we did. I'll at least erase that, and that, that, and that. So our A sub n now, and I probably can erase this down here too. Let me do that too. I meant to. We'll just leave our conclusion there. So A sub n is equal to, I'm going to put the B first, 1 over 2n minus 1 minus 1 over 2n plus 1. Right? this may make a little more sense to do our investigation on these. Let's see what a sub 1 would be. One over help me somebody. 1 minus 1 over 3 plus a sub 2. Okay, let's just do it this way. A sub 2 would be, I'll leave off the pluses till later. A sub 2 would be 1 over 3 minus 1 over 5. A sub 3 would be 1 over 5 1 over 7. A sub 4 would be 1 over 7. Okay. Picking up a pattern. Okay. When you add these together, then you get those two go out, those two go out, these two go out, and ultimately we're getting down to your S. Let's just go straight to the S. Okay. That's these are your part. Okay. When you add them all together, you get these here. So your S sub n would be 1 minus 1 over 2n minus 1. Right? That's what they were every time. And it's 1, you have this. It's 2, these will go out, and it'll be that. And it's 3, these all these go out, and you have that. 4, and so on. So, I did do, yeah, A sub 4 would do that. Okay. So, what's that doing is n goes to infinity. It's converging to 1, for sure. So, okay, it's going to 1. All right. Now, they said it was 1 minus 2n plus 1. Oh, I thought it was minus 1. I'm not sure they don't have their sign backwards. Nope. Wait. Yeah, I have mine backwards. That is a plus 1. Yeah, it's. Yeah, I was looking at the wrong line. This is the line I should have erased that line too. So, yeah, 2n plus 1. And that's still going to 1. All right. Any questions? Example 2. Let's move to geometric series. What in the world do we mean by that? Is geometry coming into play here? Well, not quite, but we'll see. Here's a series. Summation of, a series is always a sum. It's a sum of the sequence 1 over 2 to the n. So sum of n equal 1 to infinity, 1 over 2 to the n. So when n is equal 1, it's 1/2, 2 it's 1/4, 3 it's 1/8, 4 it's 1/16. We've seen this before, but we didn't name it before. Excuse me. This is a geometric series. Why do we call it a geometric series? In general, the series let's just look at this first. What do you notice about the relationship between these two terms? The terms here. Don't worry about the sum, just the terms. This one's 1/2 of that. This one's 1/2 of that. This one's 1/2 of that. So every term is a multiple of something to the next of the previous term. What we call that is a ratio. This ratio here is 1/2. So what this is, it's a summation is n equals, from n equals 0. Now this time we're starting at 0, not 1. N equals 0 to infinity of a times r to the n. The reason we should do that is so we can start with a. Okay? R to the 0 is 1. So that starts with a. The next term would then be a r to the first. So it would be a times r. That should be a times r squared, a times r cubed, a times r to n. So that's what makes a geometric series. Every term, the ratio of any two consecutive terms is always the same. Ratio between these two is r. Between those two is r. Between the next two is r. Ratio between these two is 1/2. These two is 1/2. These two is 1/2. It's always some ratio. Okay? Now, of course, this a sub 0 can't be 0. A can't be 0. If it was, this is just a 0. It doesn't make any sense. Okay? Because everything would be 0. So it's some number, non-zero number. Notice we didn't say positive or negative. We didn't say rational or irrational. Just some number, a, not 0, as long as it's not 0. And then every term is some ratio multiplied by the previous term. And that's what you're adding together. That's a geometric series. And with the ratio r, now this r can't be 0 either. That wouldn't make any sense. A, not 0, multiplied by 0 to the n, that's always going to be 0. So those would be trivial cases that produce nothing but 0. A can't be 0 and r can't be 0. Now, with that in mind, there's something else. R also can't be 1. Okay? Let's see this. Convergence of a geometric series such as this, with a ratio r, diverges whenever the absolute value of r is greater than or equal to 1. Greater than or equal to 1. If r was 1, it's going to diverge. Okay? If anything greater than 1, it's going to diverge. But if the absolute value of r is anything less than 1, okay, then the series converges, and what does it converge to? Okay? The summation of n equals 0 to infinity. A is not 0, remember. R is not 0, remember. Okay? Raised to the n would be a, whatever that constant is, in every term, divided by 1 minus that ratio. Of course, that ratio is something less than 1, so 1 minus that ratio is going to be something positive, because r is less than 1. Wait. R could be negative, but still going to be positive. It's always going to be positive. As long as that absolute value of r is less than 1. Okay? That's what a geometric series always converges to. So the first thing you do, if you have a series there, one of the first things you do, see if every term in the series has a common ratio. If it does, you've got a geometric series, figure out what the ratio is, and then go back to that first term and you can figure out what the a is. So let's see if that works. Here's example 3. Here is your, they tell you it's a geometric series, okay? The summation, n equals 0 to infinity of 3 over 2 to the n, okay? Well, that's going to be the summation of, pull the 3 out, and that's your A, and this is your R. R is less than 1, it's going to converge. What is it going to converge to? You tell me. Anybody? What did we just say it would converge to? A over 1 minus R. What's your A here? Just wrote it down. 3 over anybody? Second? 1 minus 1/2. Please don't say 1. 1 minus 1 is 0. That's not going to work. So this would be 3 over 1/2, which is 6. You got it. That's a geometric series. It converges to 6. Okay? By the way, I neglected, right after the theorem there, they have a proof for it. And actually, it's a nifty little proof. I should have probably done that. I was thinking they were going to do it. I've completely missed it. Okay? But you may have done something like this in the past. I know even at dinky little Waynesboro High School in Georgia, where I went, I had a math teacher that showed us this one. If you're, let's go back to this slide. Oh, we don't have any room on that slide. Okay. So I'll do it down here. Okay. I'll erase this later. If your S sub n, that's the partial sum, the nth partial sum, is A plus AR plus AR squared plus AR cubed plus ... plus AR to the n. Actually, n minus 1, because we're starting at n equals 0. Okay. See, this is the first term, second term, third term, fourth term. So the exponent is always 1 less than the number of the term. So that's why it's n minus 1. All right. Easy way to prove that the geometric series work. Here's what we do. Multiply both sides of the equation by r. Okay? So now we have r times s to the n is equal to AR, that's that first term times r, plus AR squared, plus AR cubed, plus ... all the way up to AR to the nth. Right? Now, I'm going to erase the times r that I put up here and go back to what we originally had. Okay, whoops, get out of there. Now, what I'm going to do is subtract the first line from the second line. So we get r times r s sub n minus s sub n. Now, yuck. Notice I set these up this way on purpose. This cancels out, that cancels out, that cancels out. All of them cancel out until, and this one cancels the one before it. So you wind up with a r to the n minus a. Right? If you subtract this line from that line. So that's a minus left here, a plus that left there. So now let's factor out the S sub n. That's what we're looking for, S sub n. Factor it out, you have R minus 1, right? Is equal to A times R sub n minus 1. Okay? Am I going the right direction on this? I think so. Let's divide both sides of this by R minus 1. Now this requires a little bit of trust here. R sub 1, R minus 1 will go into that, and okay, you know what, I think I've done them backwards. I should have subtracted this from that. Sorry about that. So okay, this is going to reverse this and this and this and that and that and that. Okay, sorry about that. Subtracting the other way, this would be S sub n minus R times S sub n is equal to A minus that. Okay. So this gave you S sub n times 1 minus R, and this was A minus times 1 minus R sub n. Okay. And we're going to divide both sides by 1 minus R. Okay. Okay. Now, what they do is separate this out, A over 1 minus R, and this is times 1 minus R to the n. And as n is going to infinity, remember R is less than 1. Absolute value of R is less than 1. Remember that. Okay. Any number less than 1 that you raise to an enormously large power is going to get closer and closer to 0. So this is getting closer and closer to 1. So there is your proof. A over 1 minus R. So as long as that absolute value of R is less than 1. So sorry, I probably shouldn't have taken time to do that. So let me erase everything on the slide. Okay. So let's see how they did it. They'll say that's 3 times 1, because when n is 0, that would be 1 over, well, it would be 1/2 to the 0th power is 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1/2 squared. Okay? So it has a ratio of 1/2. Every term is 1/2 times the previous term, and your A, the constant, is 3. So, because R is less than 1, 1/2 is certainly less than 1, the series converges. Its sum is S is equal to A over 1 minus R, 3 over 1 minus 1/2, 6. And this is what it looks like if you were to plot that series. You're going up, getting closer and closer to 6, closer and closer to 6, closer and closer to 6. After a while, you can't tell the difference. You still are infinitesimally less than 6, but getting closer to it. So you can do that on your calculator if you know how to do that on your calculator. All right. So that was example 3, the A part. Let's do the B part. Here's a geometric series, okay? The summation of 3 halves to the nth power. Okay, now how is that different from before? This would be 3 over 2 to the nth power. The 3 wasn't raised to the nth power, it's just 3. You can factor it out. This one is 3 halves to the nth power. Okay, that's going to be, when n is 0, that's 1. When n is 1, it's 3 halves. When n is 2, it's 9/4. N is 3, that would be 27/8. And 81/16. And it just keeps getting worse and worse and worse. The ratio here is 3 halves. What does that tell you? Diverges, don't even mess with it. Diverges, for sure. If that ratio is 1 or greater than 1, absolute value is going to diverge. And that's all you have to do. Just notice that. I'll erase my stuff, because the absolute value of R, that's 3 halves, greater than 1, the series has to diverge. Don't even mess with it. Okay? All right, I thought there was a C there. There's not. However, there is an example 4. So let's go back and do example 4. Now, you can also go to larsoncalculus.com for an interactive version of this type of an example. Okay? And yeah, you can do this. It says use a geometric series to write 0.08 repeating as a ratio of 2 integers. Okay? 0.08, 08, 08, 08, dot, dot, dot. So this is the part that's repeating. And it just keeps repeating and keeps repeating and keeps repeating. Now, what do we know about a decimal that has a repeating unit to it? It can be written as a fraction, a ratio of 2 integers. And this one can, that's what it's saying. So for the repeating decimal, use a geometric series to write that as a ratio of 2 integers. Okay? Meaning that's a rational number. Here's, you don't need the infinite series. You can just do it straight. Okay? Same rule we used before. This time we're going to multiply this by the number of digits, the power of 10 to the number of digits in your repeating unit. That's a 0.8. 2 digits, so multiply by 100. So you get 8, you move the decimal 2 places, 8.08080808, dot, dot, dot. Now subtract from that the original number. Now let's just call that, what you want to call it, n. Usually we use n for integers. Let's call it r. No, let's not call it r. We use r for something else. Pick a thing to call it. Yeah, I don't care what you... Q? Okay, why don't we call it Q? Why not? This thing right here is going to be our Q. Okay? So we're going to do 100Q minus Q. 0.8, 0.8, 0.8, 0.8, dot, 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 dot. Minus Q. What does this give us? When you subtract those all disappeared, you're left with 8, right? So we have 99Q, because 100Q minus Q is equal to 8. Divide both sides by 99. q is equal to 8/99. And guess what? You don't need to do an infinite series. You got it. But you did it the same way you proved the infinite series. That's why I went back and did the proof, so you could see this is the easy way to do it. Now, this is something I learned at little bitty old rural Waynesboro High School. I think it was, or somewhere back there. I learned how to do this. Same way we proved an infinite series. That is indeed a rational number, and for any decimal that has a repeating unit with it, what you might have to do, if it had something before the repeating unit, like 0.97308080808, first multiply and get the 9.8, multiply by 1,000 and get that out, then multiply by 2 more and get that, and you wind up with the same type thing. It'll just be a different denominator. Okay. Punch that on your calculator. 8 divided by 99. See what you get. Okay, you got it. What's that? Understood? Now, in the book, they did it by geometric series. Okay? And they did that by, that would be 8 over 100 plus 8 over 10 to the 4th plus 8 over 10 to the 6th plus 8 over 10 to the 8th. So they factored out at 8 over 100. It seems like to me they should have factored out just 8, and then your ratio was 1 over 100. Okay? And it gave you the same thing. I think mine's easier than that. So because you did, this was 100 cubed. Remember you said you picked cube, right? This number was cube. 100 times cube would be this thing right here. You just move your decimal 2 places. That gave 8.08. So that's 100 cubed minus cube, which was 0.08. 100 cubed minus cube is 99 cubed. 99 cubed on the wall. No, that's something else. Okay. 100 cubed minus cube is 99.
That was me.
Thought what was that?
I thought 100
Yeah, this thing is equal to 8. It's 100 cubed minus cube is equal to 8. And that's what we said. 99 cubed is equal to 8. And then divide by 99. That's where you get your 99. 100 cubed minus cube. Okay? 99 cubes. And then number 1 is a cube on the wall. Huh?
It is.
Yeah. All right. So that was example 4. Now, let's see what they do next. How are we doing on time? Not much, okay? All right, sorry. There's yet something else to do here. Let me erase what they got here, because I think the next part is sort of important. The convergence of a series is not affected by the removal of a finite number of terms from the beginning of the series. For instance, this geometric series. Not doing this. They may pick it up later, but here it is. The summation from n equal 4 to infinity of 1/2 to the nth. Okay? And the summation of n equals 0 to infinity of 1/2 to the okay? They both converge just because you converges, right? And it does. The A is 1 and R is 1/2. That converges to 1 over 1/2. That converges to 2, right? Now, just because you dropped off the first 4 terms, that's also converges because, guess what? That converges as fewer terms, and this one with more terms. This one with fewer terms is going to converge as well. So all you have to do is add up this first 4 of those. That would be 1 plus 1/2 plus 1/3. I mean, what? 1/8 plus 1/16. Add those together and subtract it from 2. And you've got what the answer is. So this is 2. We just did that one. Okay. And this would be that same thing, only what you're missing here is 1 plus 1/2. That's the second term, plus 1/4 is the third term, plus 1/16 is the fourth term. Well, we already did what this is. This is, we did what this is. This is 3/4. Add 1/16 to it, it would give you, wait, I left off 8. I'm sorry, that's an 8 there. This would give you 7/8. So it would be 1 7/8. So 2 minus 1 7/8 would be 1/8. Okay. So just because you leave off a few terms doesn't matter. It's still going to converge. Now, they have a little blurb remark there. In words, Theorem 9.6, which is the previous one, said that the sum of a convergent geometric series is the first term of the series divided by the difference of 1 and the ratio. So that's a really easy way to say it. So let's now move to Theorem 9.7. Do we have time for this?
Yeah,
1 minute. Let's start with there next time. What you say? So we will start top of page 603 next time. And let's see how far. Oh, look how close we came to finishing 9.2. Think you can do any of the odds, 5 through 9. They're all at Calc Chat. Well, I'd say do 5 and 7, either 5 or 7 first, and then try number 9. They're all at Calc Chat. Then do any of the odds 11 through 17. They're all at Calc Chat. 11's at Calc View. Do any of the odds 19 to 23. They're all at Calc Chat. 19's at Calc View. Try either 25 or 27. They're both at Calc Chat. 29 through 37 should all be at Calc Chat. 33's at Calc View. 39 to 43 are all at Calc Chat. 39's at Calc View. And you can do that either way we did it or other. And then we'll pick up the rest of those next time, I believe. Good deal. Any questions? All right. Glad y'all didn't take the Veterans Week vacation and just took Veterans Day vacation, but a few others. Well, actually, I know that Fred is going to be out of town. Is he a NASA thing? Huh? I think so. Yeah, Dr. Thomas is with them there. Nice trip to California. I think it's with STEM. I was going to say it was with NASA, but I believe he's on STEM. But he's reporting on some of the stuff he did with NASA. All right, good deal. All right. Good deal. Let's end it.